Y'all,
Send it in an email.
He didn't say there was a test. He said it's doing stuff that we go
Alright,
over next
good
week.
afternoon.
he never says when you have to.
You gotta consider it you gotta be rolled up in the test.
Fine. Danielle, if we show up to class on Monday and you leave, we're gonna be like, no,
Any
that's your
questions before we start? Today we are gonna finish velocity analysis. Then next week we are gonna start acceleration analysis. On Monday and Wednesday, Thursday we are gonna have the exam. And after that we are gonna talk about force analysis. All right. The last mechanism that we cover, we go over velocity analysis is in inverted slider crank. Inverted slider crank is a mechanism like this. To perform velocity analysis, we need first to do displacement analysis or position analysis. In position analysis, the constants are A, the length of this length of the second link, B is not constant, C is constant, and D is constant. And gamma also is constant. The angle between link 3 and link 4. It has been fixed, so we only have translational motion. Variables are theta 2, theta 3, theta 4, and B nouns are constants plus theta 2. 1 degree of freedom, so we should know one of the variables as a given or as input, which is theta 2 here. We are solving for unknowns where whatever left, theta 3, theta 4, and B. We can get two equations, but we have three unknowns. We know that theta 3 is theta 4 plus gamma. So basically we have two unknowns we can solve for that. And the vector loop equation would be thank you. It's gonna be O to A. This is the point with two arrows into that. I'll stop here. Equals to O2, O4, O4B plus vector BA. This is what we did. In this displacement analysis, the x component is going to be A cosine of theta 2, A cosine of theta 2 for this vector equals to O2, O4, D. D cosine of 0 or the x component is D. C cosine of theta 4 plus B cosine of theta 2. And y component is A sine of theta 2 equals to, there is no y component, or D sine of 0 is 0, C sine of theta 4 plus B sine of theta 3. And then after we are done with displacement or position analysis, we can do velocity analysis. Whatever was variable here, just put a dot on top of that. V dot, theta dot 2, theta dot 3, and theta dot 4. Theta dot 2, theta dot 3, theta dot 4, and V dot. Just put a dot, or how this variable are varying with time, or omega 2, omega 3, omega 4, and V dot. And nouns would be constants plus. We are done with the displacement analysis, so all values of theta 2, theta 3, theta 4, and V are noun plus here theta 2 was given for the noun, theta dot 2 also should be given. So we should know what would be the input velocity of this link at when the link 2 is at the angle of theta 2. So omega 2 should be given. We are solving for theta dot 3, theta dot 4, and V dot. Is that clear? All right. Here you can see the displacement equation. I'm gonna derive the velocity equation. So as a class activity, just differentiate the first equation and find me the first equation for velocity. I'm gonna do the second one by myself. So I just want to make sure that you know how to do differentiating of the equation. Fair enough? Yes.
The first, sorry.
I'm asking you to differentiate the first equation with respect to time to get the velocity equation. So just work on the first one. I'm gonna call from class list.
What's the difference between B and B dot?
What's the difference between
B and B dot?
V dot is the velocity, and V is this distance, it's a length.
Yeah.
V dot is how fast this length is changing, the velocity of changing. Number 4.
So, negative 8, so sine theta 2 times theta dot 2.
Okay. Negative a theta dot 2 times.
Sorry, negative a sine theta 2 times theta 2 dot equals negative c sine theta 4 times theta 4 dot minus b sine theta 3 times theta 3 dot.
Thank you. Number 27. Okay, what do you want to change that or?
No, I think that looks pretty good.
Okay, thank you.
Yeah.
One more. 34. Do we have? Jeff.
That's not here. Yes, was that
I think
math
he said he
about?
was going. He told you yesterday it was going to be at the conference.
Number 3. Number 28. Julia, yes. Do you want to change this or you agree with this one?
I like that.
When did you add the plus b dot sine theta 3?
There is one more term. In previous mechanism, the length of the links were constant. So when you differentiate them like C, like A, they are coming out of the derivative. But here, B is varying with time when the mechanism is moving, as well as theta 3. So derivative of multiplication of two functions, it's going to be derivative of the first term times the second term plus derivative of the second term times the first term. So we already have the derivative of second term, which is cosine of theta 3 times first term, but I should add b dot derivative of the first term times cosine of theta 3. Good? Everybody can see that. How did we add this term? So this is the first equation. Second equation, derivative of first term, a is constant, derivative of this with respect to time. This is not time. I should use the chain rule. It's going to be a cosine of theta 2, theta dot 2, left side. C is constant. C cosine of theta 4, theta dot 4, plus B is varying. B dot sine of theta 3 plus B cosine of theta 3, theta dot 3. I already have, yes.
If you used to add the gamma plus theta 4, would it now be easier when you just take out theta 3?
It's gonna be the next step.
Oh, okay.
I didn't want to confuse.
Yeah, okay.
So the first equation you can see here, negative a sine of theta 2, theta dot 2, or you can change the order. Right side, this term, b dot cosine of theta 3 minus b theta dot 3. And second equation you can see a theta dot 2 or a omega 2 cosine of theta 2, c theta dot 4 cosine of theta 4, plus these two terms. Good? Any question on this? All right, I have two equations, but I have three unknowns. Can you tell me how can I connect these two? What would be here? We have the relation between theta 3 and theta 4. What would be the relation between theta dot 3 and theta dot 4? Say it again.
Theta 4 minus theta 3 again.
Theta 4 minus theta 3 equals to gamma.
Or theta 3 minus
Yeah.
Yeah.
Now I'm asking the correlation between theta dot 3 and theta dot 4. They are equals. If you differentiate both sides, this side it's going to be theta dot 3, theta dot 4. Gamma dot is not changing with time, so it's going to be 0. So basically, if you move theta dot 4 to the other side, the angular velocity of link 3 and link 4 are the same. Makes sense?
Is this the second one? The derivative of the
This one,
y component?
y component, second line,
Yeah.
b dot sine of theta 3 plus b theta dot 3 cosine of theta 3. These two, if you can see. Yes. Question. Now I'm rewriting these two equations. This time I'm gonna replace theta 3 by theta 4 plus gamma. So, and theta dot 3 yeah, I replace theta dot 3 with the theta dot 4. So you don't see any theta dot 3. So here minus p dot, instead of having theta dot 3, I'm going to change it to theta dot 4. If I want to rewrite it again, I'm going to rewrite that term again. Negative c sine of theta 4, theta dot 4, the first term. Negative b sine of theta 3 is going to be theta 4 plus gamma, and theta dot 3 is going to be equal to theta dot 4. It's going to be this term, and b dot cosine of theta 3, or b dot cosine of theta 4 plus gamma equals to negative a theta dot 2 sine of theta 2. Second equation is going to look like this: c cosine of theta 4, theta dot 4 plus b cosine of theta 4 plus gamma theta dot 4 plus b dot sine of theta 4 plus gamma equals to positive a theta dot 2 cosine of theta 2. Now, just don't get confused. The unknowns are theta dot 4 and b dot. They cannot be more than 2 because I have 2 equations. And you don't see any theta dot 3 here. So any term with theta dot 4 and b dot should be kept on the left side, this term, and this term. And the constant part should be moved to the right side, which is this one. So now form the matrix A, matrix X, and matrix B. Here I'm gonna write the unknowns, which are theta dot 4 and b dot. It doesn't matter which one goes first. Here I have b dot and theta dot 4. I can write theta dot 4 first and then b dot. So I'm following the way that we have on the slides. So first row corresponding to the first equation. Whatever is the coefficient of B dot is coming here, which is cosine of theta 4 plus gamma, or cosine of theta 3. Second term, whatever is the coefficient of theta dot 4. This is theta dot 4, this is theta dot 4. This plus this, negative C sine of theta 4, negative B sine of theta 4 plus gamma, which is this. Right hand side, I'm going to have negative A theta dot 2 sine of theta 2. Second row, second equation. The coefficient of B dot is sine of theta 4 plus gamma. Coefficient of theta dot 4 is this guy plus this guy. C cosine of theta 4 plus B cosine of theta 4 plus gamma is that. And right side is going to be A theta dot 2 cosine of theta 2. A and B are coefficient and constant matrix. You can use the MATLAB. A backslash B is going to give you the result.
This will not be enough for stats, right? Just position analysis?
Just displacement analysis and whatever before that. No velocity.
What about without using MATLAB? How can you do that?
I'm not asking you to use the MATLAB, but you should have your calculator and know how to use the calculator too. If it's written.
So just displacement analysis?
Any question about this? All right. Now, we will see how can we find the velocity of any desired point. For example, this point. I would like to find the velocity of point P when this mechanism is at the angle of theta 2 and velocity and input velocity is theta dot 2. How can I do that? So we are gonna learn about that. You already know, we just want to practice. Suppose we have this 4-bar mechanism with this terminal link. This angle is delta, this angle. The other angles are labeled as theta 2, theta 3, and theta 4. Suppose this input link is at the angle of theta 2 and the angular velocity of theta dot 2. We would like to find the velocity of point P. find velocity of point P or any other point. Point P is just a point that I picked in this mechanism. It can be any point. To do this, first you need to do perform displacement and velocity analysis. When you perform displacement analysis, you find theta 3 and theta 4 by performing displacement analysis. Theta 2 is given, you are solving for theta 3 and theta 4. By performing velocity analysis, you find theta dot 3 and theta dot 4. Just put the dot. Then try to reach point P or any other point from the origin, which is O2, by adding the vectors. So if I want to start moving from point O2 and reaching to point P, I should have this vector plus this vector, or I should move along this path. This vector plus this vector plus this vector. I mean, it doesn't matter which way, which path you take, but you should reach to point P by adding the vector. So vector O to P is gonna be O to P. Is gonna be O to A plus AP, or O to P would be O to O4 plus O4B plus BP. Either this one or the second one, it's gonna be the equation that you are gonna use. Point O2 is the origin. So x component of point P, x component of point P would be the x component of vector O to P. This is the vector O to P, so x component of this is going to be this. Right hand side would be the x component of O to A, which is A cosine of theta 2. This is A, this is B, this is C. This length is RAP. The length is RAP. Plus the length of the vector multiplied by cosine of this angle. Cosine of this angle times RAP is going to give me the x component of this vector. This angle is theta 3 plus delta. So I'm writing RAP cosine of theta 3 plus delta. So that's going to give me the x component of point P. Y component of point P just change cosine to sine. This is how you can find x component and y component of point P. Now, if I ask you find the velocity of point P, you are looking for x dot P. X component of velocity of point P is going to be how fast x coordinate is changing with respect to time. So we differentiate both sides. d of xp with respect to time would be derivative of the first term. A is constant, theta 2 is varying. Negative a sine of theta 2, theta dot 2. RAP is not changing. The length of this this length of this link is not changing with time, so it's coming out of the derivative. Derivative of this, negative sine of theta 3 plus delta multiplied by derivative of theta 3 plus delta with respect to time. This is not the time, but it's varying with time. We are using the chain rule. So multiplied by this. And this is going to be derivative of theta 3 with respect to time plus derivative of delta with respect to time. This delta is not varying with time. This angle is fixed. It's part of this rigid body. So it's going to be 0. So we are going to get only theta dot 3. So x component of point P, velocity of point P in x direction is gonna look like this.
And it's negative, right?
Yes, the derivative of cosine, the derivative of cosine with respect to theta 3 is going to be negative sign. Here, look at the first row. A cosine of theta 2 plus r of PA or AP, cosine of theta 3 plus delta. Here we have delta 3. It's going to give me the x component of point B. If I differentiate that, I'm going to get this term. For this, RPA is constant, is not varying with time. It's a coefficient coming out of the derivative. Derivative of this is going to be theta dot 3 times sine of theta 3 plus delta 3. This is how you can find the velocity of point P. In x direction, do the same thing for y component. You can get the y component of velocity of point P. I could ask you find the velocity of point B or find the velocity of any other points. What you need to do, just try to reach to that point by adding the vectors and differentiate, and then derive the x component and y component of that point, differentiate both sides, find the velocity. Any question on this? Yes.
So for once you did the derivative of theta 3 plus delta.
Okay.
Okay. What did you get? What were you adding?
In here,
Yeah.
the derivative of two terms. It's going to be derivative of the first term plus the derivative of the second term.
Yeah, I was asking like, what did you add to the derivative of x and b? The dot.
Or here.
Yeah, like what did you add on to the equation again? Once you finish that.
Okay. Here I have multiplied by derivative of this. Okay. And I replace this by only theta dot 3. I replace the entire of this with the theta dot 3.
Alright.
Make sense?
Yep.
It's very important because we are going to use this on acceleration as well. When we perform acceleration analysis, the last thing that we cover, find the acceleration of any desired point on the mechanism. And why we care about acceleration? Because force is going to be the mass times acceleration. If you know the acceleration of the point, if you know the mass, you will see how much force is going to apply to the rigid body when the mechanism is moving. Good? All right. Before, I'm going to look at the homework 7, but before we go through that, let's have a quick review on what we covered on velocity analysis. On velocity analysis, the first thing that you should do is displacement or position analysis. It should be performed first before you go to the velocity analysis. how can we develop or derive the velocity equation? You should first get the displacement equation, and then differentiate both sides with respect to time to get the velocity equation. Displacement equation are non-linear, but velocity equation are linear in the unknown variables that we are looking for. So it's the reason that we can solve simply by the matrix form by using the method. And whatever on 4-bar mechanism, we pick theta 2 as the input, we solve for theta 3 and theta 4. Any variable that you pick as an input, its derivative should be picked as an input for velocity analysis. So if you pick theta 2, theta dot 2 also should be picked for input under velocity analysis. So this is the homework. I changed the due date to Friday. Thursday we have exam, so I decided to move it on to Friday.
So it's the 25th now?
Yeah,
Could you change it from Thursday the 24th to Friday the 25th?
25th.
Okay.
It's Friday. The Friday is, I'm gonna revise that and post it again. First problem is asking you to do velocity analysis for row A. 6.5 is a 4-bar mechanism. And you need to submit by the MATLAB in 5. I removed that one because we didn't cover the displacement and velocity analysis. Problem 6.9, it's about inverted slider crank, submitted by the MATLAB. I'm gonna talk about problem 3 and 4. Problem 3 you have done for displacement analysis. Now I'm asking you to do velocity analysis by providing the information coming from displacement analysis. So what you need to do, you need again write the vector loop equation, differentiate to get the velocity equation, and then solve for the unknowns. Just same as the mechanisms that we did in the class. So 4-bar mechanism, offset the slider crank, and inverted the slider crank. So this is the easy one. This is going to be more this is the mechanism that you did for displacement analysis. Now I'm asking you to do for velocity analysis. Exactly the same step that you did for displacement analysis, you should perform here for velocity, except you should differentiate displacement equation and solve for unknowns on the velocity equation. Solve for the unknown on velocity analysis. I already provided the information for that you need for velocity analysis. This information coming from displacement analysis, so you don't need to solve for displacement. I already provided them here for. For example, here I said phi3 is 0.41 radian. The angle is radian, and phi3 is the angle of CB with the ground line. Let's look at the CB. This angle is 0.41, not this angle, because this is more than 0.41. Again, so when I gave this, I meant this kind.
We're considering just the one mode, right?
Yes, I already provided the location of all links
Okay.
and sliders, so we don't perform the displacement analysis. I already gave you which mode I mean. All right, any question about this? I'm gonna post a sample exam as well. The first exam is gonna look like, the first problem is always having finding the degree of freedom for some given mechanism. I am asking you to label all links and joints. How many links can you see here? How many joints can you see in each mechanism? After you find them, find the degree of freedom based on number of links and the number of joints. This is the first problem that you will see on the exam one. Yes?
Are you going to post a solution for that?
For this, I can do that.
Not that,
Yeah,
not
no.
that, that one.
This one. This one. Yeah, I can post the solution for this. Sure. Last year, I mean, it was 2 years ago. This is for 2 years ago. That was it. You are given with the crank rocker mechanism, and the length of the mechanisms are given. On first part, I'm asking you find the input angle in which the transmission angle is 90 degree. So at which input angle the transmission angle is 90 degree. And second one, find the mechanical advantage of the mechanism at this position. So and last problem, there were 3 problems. In this offset slider crank, we always are given with theta 2. Here in this problem, I gave you the location of a slider. I asked you to solve for the other 2 variables. So the location of a slider was given. You are solving for theta 2 and theta 3. I like this problem because it's doable in 1 hour exam. You have to derive the displacement equation and show how you can solve the system of equation for other 2 and not. I'm not going to give you this one, but for the exam, but I like that. The exam, I'm going to send email, but the exam would be on Science Center Hall room. So I'm going to start the exam at 2:10. Next Thursday, 2:10.
Most of us get thermodynamics, the class before this.
Okay. Just run to the exam. I'm gonna give you 5 minutes more after. Make sense?
I got out of class at 2:15. So like, you don't have to go at like 2:10, right?
No, I mean, the exam would be from 2:10 to 3:15. So 65 minutes, 5 minutes extra. So if you come later on, do your best to come in. At least for 1 day. Alright, any question? Yes.
Can we make like an equation sheet or no?
Oh, it's a good. So you can have 1 sheet both sided as a equation sheet. It's a closed book, but you can bring one sheet as a question. Yes. Yeah, closed book, closed notes. Prepare yourself very well for the first exam. I don't lower my standards for passing this course, so and I don't mind. I would like everybody to get a good grade, but I don't mind if I need to fail as many as needed. I don't want to scare you. I mean, I just want to.